So a sequence is defined as a function whose domain is the set of positive integers. One, two, A1, A2, A3. All the way until A7. So these right here are the terms of the sequence. A sub n denotes the nth term. So A sub n, and is also, I guess, another way to say it, the name of the sequence. Just real quick, just so we get comfortable with the notation. Find the first 5 terms. First 5 terms. So we give you a sequence called an, and n squared over 2 to the n minus 1 is what it does. And remember that the domain will only be positive integers 1 through infinity, right? So the first term would be denoted as a1, which means you plug in a 1. And you get 1 over 2 minus 1. One half, right? Is that right? No, that's not right. 2 minus 1 is 1. Right? So that is my first term, a sub 1. A2 would be plug in the 2 to the that'll be 4 over 4 minus 1, which is 4 over 3. So then you keep going till you find all 5. Do you see a pattern? Or no? If you don't see, we can keep plugging them in, right? It'll be 16 over 16 minus 1. Root of 4 is 16 minus 1, 15. Right? 4 squared 60. Let me show the step. Okay. Anyway. You understand what we mean by a sequence and what the a sub n stands for. Let's see how A1, A2, A3. I want to make sure you understand the notation. Let's skip the fifth one. I don't really care about it. I'm going to give you a note. Do you guys remember what factorials are? So an n be a positive integer. Yeah, of course. Positive integer. Then n, and then n factorial is defined as n with the exclamation point. That means factorial. That means you multiply from 1, 2, 3, 4, all the way until you get to the n. So for example, 3 factorial means 3, 2, 1, which is 6. 5 factorial is 5, 4, 3, 2, which is what? Got 120? Right? Yeah. That's what factorial means. You should have seen it in college algebra, but sometimes you don't. But that's all you need to know. One extra thing is note 0 factorial will always be 1. It's definition. Okay. All right, so let's move on. Let's do an example with factorials. Any questions on this so far? You guys cool on this page? Simplify the ratio of factorial. To 1 factorial over 2n plus 2 factorial. So you agree that the one on the bottom is just 2 more than the one on the top, right? And we also said that, so I'll leave the top alone. If I start to expand the bottom, right, we're going to get to go all the way down from like this 5 factorial to 5, 4, 3, 2. So if it's 2n plus 2 factorial, you start there and you subtract 1 for the next one, subtract 1 again, you get to here, right? And then I can just stop because it can go on forever. You agree? So then these will cancel. So that would be 1 over 2n plus 2 times 2n plus 1. Does that make sense?
Can you describe that again? How you separated the bottom?
What's that?
Can you describe again how you separated the bottom?
Yeah, I guess let me give you a number example, and then we'll come back to it. Let's say we had 20 factorial over 17 factorial. You agree that this would be 20 times 19 times 18 all the way down to 1, right? This would be the same thing starting at 17. So if I start the top part out, let's stop at 17 instead of going all the way, then I can cancel it with this one. See what I mean?
Oh, I see.
So that's what we did here. We said, well, it's 2 more than the top. So if I expand it 2 times, I can cancel that guy. So now there's no more factorials. That's just some number. That's another example. You're right. I just want to make sure that you're comfortable with factorials. It has nothing to do with sequences yet. I want to make sure because I feel like you guys don't remember factorial. Okay. Anyway, let's get back to sequences. Definition. The limit of a sequence. So let L be a real number the limit of a sequence, which we will call A sub n, is L, written as the limit as n approaches infinity of A sub n is equal to some limit L. For each epsilon greater than 0, there exists now capital M greater than 0, such that the absolute value of A sub n minus the limit L is less than epsilon. Whenever n is greater than n. Well, the main thing that you need to know is right here. If the limit exists, then the sequence converges to L. So this is the main part that I really care about. If the limit does not exist, then the sequence diverges. So in this section, what we're going to be doing is we get a sequence and we need to figure out, does it converge or diverge? And the only way to tell is to take a limit and see if it's finite. Not finite, well, diverges. So all of chapter 9 is going to be the same question. Does it converge? Does it diverge? Over and over again. You need to explain why or why not. Oh, wait a second. And we find that first example here. Well, because I should write the properties from Cal 1. Do you guys remember your limit properties? I'm going to write them down just in case. So let a sub n, well, let the limit of a sub n equal to L, and the limit of B sub n equal to K. Number one, first property, called the scalar multiple. The limit of C times A sub n as n approaches infinity is equal to C times L. C is an element of the real numbers. Right, so basically, if the limit is equal to L and you have some number on it, you just multiply that number on it. So that's what scalar multiple is. Just multiply it out. You can also pull the C out here technically. We're not going to do that. Sum or difference. So if you're summing, let's say A sub n plus or minus B sub n, as n approaches infinity, that's equal to the limits added together or subtracted together. Right, because they're right here. And the last two is a product and quotient. The limit of A sub n times B sub n as n approaches infinity would simply be L times K. And the last one limit as n approaches infinity of A sub n over B sub n is equal to L over K, where B sub n is not equal to 0 or K is not equal to 0. All right. No rush. You guys cool on this page or not yet? Okay, so let's wait a bit. Now we'll start some examples finally.
Can you go back on the first page that you guys work on real quick? So I can take a
Yeah, sure.
shot.
Did you miss something here?
Yeah. Like all of it. Is it possible you can zoom out a little?
Maybe, let's see.
That's fine.
Oh, no.
I guess, yeah, I guess I can do that.
That's everything right there.
Sure. Oops.
You said quotient is Bn plus minus or?
Yeah, Bn cannot be zero, not zero. Okay. That's cool. So goal of this whole section is to check, you check the limit of the sequence and you see if it converges. So determine if the sequence converges or diverges. Well, no, it's not really going to start like that, I guess. It's only going to say A. That's the first step. They're going to give you a sequence. You need to determine, does it converge or diverge? The only way to tell is to take the limit as n approaches infinity and see what the sequence does. Now, back in count one, we showed the work, right? We said divide each term by the highest power. So that would be 3 over 1 plus 5 over n. This will go to 0. So the limit will be 3. So the conclusion is the sequence converges. Because the limit is finite. Because the limit exists. If it doesn't exist, you would say diverge or if it's infinite.
Okay, so. So if the limit goes to 6, then
It diverges.
but the result will be 0, right?
The limit would have to be like infinity or negative infinity. But there are times where I think if it's infinite, then it diverges. I don't think you're going to see anything that doesn't have a limit. Trying to think of an example. Yeah, actually, there is one. There is one. I'll show you in a little bit. But you see that the n squared was the highest power, right? So all I have to do is look at the 3 and the 1, right? And divide it. Divide 3 by 1. You're good. That's it. Okay. Determine if the sequence converges or diverges. A sub n is equal to n over n plus 1. So if I take the limit of a sub n as n goes to infinity, you can see that the limit will be 1, right? These overpower each other, so you divide by the coefficients. So 1. So the series converges. That's what we said in the definition earlier. We said if the limit exists, then the sequence converges to L. So we can say that series converges to 1. Based on the definition. Now let's do one that doesn't have a loop. So let's say you had a sub n equal to -1 to the n times 3 over 3n squared over n squared plus 5. What is this -1 going to do? All right, let's plug in some numbers. A sub 1 is going to be power 1, so it'll be -1. 1 squared would be 1 times 3 over 1 squared plus 5, right? So 1 plus 5. A2 will be squared, so that'll be a positive 1 times 3 times 4 over 4 plus 5, right? But do you see the problem? As n goes from 1, 2, 3, 4, it's going to go from positive to negative, right? So we did the limit. It would not exist because it's going to be alternating forever. As n goes to infinity, you divide these guys out, right? So it's going to be 3, but then it's going to be or -3. So you keep doing that forever. So limit doesn't actually exist. Did I write that properly? So therefore, the sequence diverges. So if the limit is infinite, or if it just doesn't exist, you would say it diverges. But it doesn't stop at a value. It's going to keep changing. Negative, positive forever. So even if it approached a number, this messes it up. Is that clear? You guys go on this page? We use some extra theorems and then we'll move on to a new section. This is the squeeze theorem. Some books call it sandwich theorem, whatever. Or sequences. So if the limit as n approaches infinity of a sub n is equal to L, which is equal to the limit of b sub n as n approaches infinity, and there exists an integer n such that a sub n is less than or equal to c sub n, which is less than or equal to b sub n. For all n greater than n. Then the limit of c sub n will also be equal to L. That makes sense what they're saying? So if you know the limits on either end, and it's squeezing the Cn in the middle, then it will be equal to the same. Okay. This is how they came up with that. Do you remember this? The limit of yeah. Number one. Absolute value theorem. For the sequence a sub n, if the limit as n approaches infinity, the absolute value of a sub n is equal to 0, then the limit of regular a sub n would be 0. Last one, and then we'll move on to a new section. Definition. Monotonic sequence. A sequence a sub n is monotonic when its terms are non-decreasing. Basically, it's like this. If you see the terms getting bigger and bigger, all the way to a sub n, I guess, or constant / decreasing. I said non-decreasing, which is weird. It's the same as saying increasing. I'm sorry. I didn't mean to be weird about that. Like purposely confusing. It was not my intention. Already difficult enough. Some math books are like that. I like reading them. Constant or decreasing, meaning A1 is greater than or equal to A2, A3, Okay. That's pretty much it for 9-1. Any questions on sequences? We'll do 9-2 and maybe 9-3 today. We'll see. Let's take a 10-minute break real quick. Or maybe 5 or so, whatever. Oh, 9-2, sorry. So the rest of the chapter is going to be about series. So we introduced sequences for a reason, but series is what we're going to be focused on. So series and convergence. So the sum of an is equal to a1 plus a2 plus a3 plus a sub n plus. So all the series, you guys are familiar with the summation notation, right? We talked about it, chapter 7, I think, or 8. I don't remember. Anyway, so all you're going to do is you take the sequence and you sum the terms. So this is the first, second, third. Before it was just a collection of terms. Now we're adding them together. So this is an infinite
Is that convergence? Like
convergence. Yes.
GE, okay.
Okay, so that's the notation. Remember we said this is the index from n equal to 1 to infinity sequence. You're adding the terms of the sequence. Capital S sub n is equal to a1 plus a2 plus a3 all the way to an. This is called the nth partial sum. Definition. Convergence and divergence let me phrase that better. Convergent with a T and divergent. Series. So for infinite series from n equals 1 to infinity of a sub n, the nth term, I should say the nth partial sum, is S sub n equal to a1 plus a2 plus a3 all the way until an. So the idea is if the sequence of partial sums converges, then Converges to, oh, actually, to be specific, converges to capital S. Then the series of a sub n from n equals 1 to infinity converges. So the limit S is called the sum. Sum of the of the series S. Where S would be equal to, I'll put this in plain English in just a moment. Also, if Sn diverges, then the series diverges. So all we're trying to say here, this is a formal definition from the book. In plain English, we're saying that if there's a sum, so if you take all the sum, all the terms from 1 to n, and you add them up, that sum exists, and it's finite, then the limit exists. So if there is no sum, meaning you have an infinite number, so that means it never converges, right? So you keep adding, and the number turns out to be infinity. So if the sum diverges, so does the series. So if the sum exists, then the series converges. It must. That makes sense? This chapter is very more math theory, I guess. Yeah, solve it. Problem solve. So to do well here, just make sure you understand the definitions. Okay. When does a sequence converge? When does a series converge? And I'm going to give you a bunch of different tests to figure out when the series diverges or converges. Okay. The first example. Oh, I just need to give you another formula. This kind of series right here is called a geometric series. So n starts at 0 to infinity. So AR to the n is equal to A plus AR plus AR squared plus AR to the n. A cannot be 0. So they all have a factor in common pretty much. It's just basically increasing something by a factor of r. So this is called a geometric series. R cannot be 0. This is the requirement for geometric series to converge. A geometric series converges if the absolute value of r is less than 1 and diverges when R, that's the value is greater than or equal to 1. It will converge to a sum should we just go ahead and write the whole thing here? The geometric series looks like this. The sum would be a over 1 minus r, where r must be less than or equal to 1. Sorry, less than 1. So this is kind of like a extension of the partial sum idea. So basically, the geometric series will converge if the r is less than 1, meaning it converges to a sum. And the sum is this right here. You can find the sum by using this formula, where a is that first term or the factor, and r is what they all have in common.
The last expression at the bottom, a over, is it absolute value of negative r?
This one,
To your left a little.
this one,
Yes. Or is that
that's a divided by 1 minus r.
1 minus r? Thanks.
Yeah. No, this is a comma. No, wait a sec, because I know that's a lot of definitions. You guys cool on this page? All right, let's get into some examples using geometric series types. Determine if the series converges / diverges, and find the sum. Should say a geometric series. Find the sum if it converges, of course, right? You cannot find a sum if it doesn't converge. Here's the series. So what is the R? Can you tell?
divided by 5.
Yeah, R is 2/5. It's the same thing, right? So you agree that that is less than 1? So since R is less than 1, then the series converges. So that would be what you would answer on the exam. You explain why. Tell me if it converges or diverges, right? Now the sum is found by doing this. So A is 4, 1 minus 2/5. And so I'm gonna write the A here. And the R is right there. So that will be 4 over what, 3/5, which is 20 over 3. Yeah, that's it. So this is the sum. So the sum, just to put it in, make it a little clear. Sum of the series is equal to 20/3. Any questions on this example?
Nope.
We have to explain if it converge or diverge and make it small, right? Yeah. On the test.
Yeah, so but I recommend you do it on the homework too, just so you practice. But what you want to do for the exam is justify or prove why it converges or diverges. So you need to say by this theorem, right? You would say, to say more properly, I would say, let's make this more clear here. Solution, right? For the justification, the series four times 2/5 to the n converges by the geometric test. Since R is less than 1, this is a convergent geometric series. So we can consider the geometric requirement at one of the first tests that we're going to look. You can have a bunch of different ones. So the hard part will eventually be figuring out when do I use what test, just like when we're doing integration, right? When do I use which technique? You know, you're gonna have a bunch of tests. Okay. Let's move on to the next part. Okay. Let me give you properties of infinite series. Let the series A sub n and B sub n be convergent series. And let A, B, C be real numbers. If the series A sub n equal to A and the series of B sub n is equal to capital B, then the following is true. So number one, series from 1 to infinity of C times A sub n is equal to C times A. So similar to the limit properties, right? Number two, if you were to add them together, A sub n plus or minus B sub n, that will simply be A plus or minus B. I think it's still 9.8. The limit of the nth term of a convergent series. So if A sub n from 1 to infinity converges, then the limit of the sequence, the limit of A sub n, the sequence, is equal to 0. So this is important right here. Right, so remember, you can't say the other directions. I don't know if you guys are studied logic or not, but this is a if-then statement, right? So if this is true, then this is true. I cannot say the other way around. I cannot say if this is true and then I can say that is true. See what I'm saying? Don't make that mistake. So what you can do though, which I'll explain in the next definition, if this is not 0, then this is not convergent. That's the next theorem we're going to make based off, I think it's called the contrapositive of the if-then statement. You switch these and negate them. So if not 0, if not this, then not this. Okay, so no, wait a second before I write that next part. The old school mathematicians were lawyers, so they would do math on the side. They needed all the logic, I think, for contracts and statements. It all has to be perfect. So understanding logic is very helpful in both being a lawyer and understanding that.
Our logical order.
Yeah. A lot of people don't understand logic. And you hear it when they argue with people. It doesn't make sense. If you understand the statement, why wouldn't be arguing?
They have to prove what they say. They have to go back.
Or they think if it works this way, then automatically it works the other way. No, that's not true. If A implies B, it does not mean B implies A. It's not true. It could, but it's not guaranteed. If you assume it does, then you get into trouble.
Under the summation is A equal to what?
Over here,
And
number one.
no, it's on the second one.
Oh, here, should have, I think that's mirrored it, huh? Should have been a one, right? I know the, yeah, logic becomes important in programming and circuitry. The on and off is true. It's very important. This whole algebra based on logic, which is called the Boolean algebra. Yeah, 0, 1 triples. But the guy who made Boolean, he created the mathematics like 500 years ago, so there was no use for it. Like there was no circuits, you know. So like now it's pretty awesome. Yeah, so that happens a lot. A lot of people go in this weird path studying math and nobody uses it until later. Like what's his name? Gauss didn't create a lot of the physics for magnetic fields and physics too. A lot of that stuff wasn't important until somewhat recent. Yeah, it was sharp. He has the nickname of Prince of Mathematics. Okay. All right, next theorem. 9.9. Nth term test. Straight mark. For divergence. So this is a consequence of the last statement I made. So it comes from the contrapositive. So if the limit of a sub n is not equal to 0, then the limit of a sub n as n approaches infinity. Sorry, that's a mistake. Just repeated myself. Then the series n equal to 1 to infinity of a sub n diverges. So this is the first test you should use whenever you're dealing with a sequence, with a series. So if you have a question, first thing you do is check the limit of the sequence. If the limit is not 0, or if it's not finite, if it's anything other than 0, you're done. Series diverged, you're done. If the limit is 0, then you know nothing. You need to go to the next test. Figure out a different technique. So it's great when it's non-zero. Okay. Okay, so let me put that in writing for you. So if this is a note for you, if the limit of a sub n is equal to 0, then the series of a sub n may or may not converge. We have no idea. If the limit is not 0, then it diverges and you are done. Let's go on this page. All right, so that's it for 9.2. We're going to use all those ideas throughout the next few sections. Let me start 9.3. We're a little behind, so can't let you out early today. No more line paper. I have dotted paper. Graphic. So 9.3 is the next test. This is the test that you don't want to use unless you have no other choice, because it requires an integral. Integral test and p-series test. So once we get towards the end of chapter 9, and you have all kinds of sequences or series, I should say, try to use every other test, and if you get desperate and you say, you know what, I don't know what to do, that's when you do integral. But if the integral is impossible or super difficult, then it's probably not the right test. Because sometimes integral is really difficult, as I'm sure you're aware. Okay. Integral test. If f is positive, continuous. Remember, all this is required to use the integral test. And decreasing. For x greater than or equal to 1. And a sub n is a function of n. then the following is true. Series a sub n and the integral from 1 to infinity of f of x dx either both converge or diverge. Remember at the end of chapter 8 we did the improper integrals, right? So that's basically what this is. You're checking to see if it converges. So you take the series right here and you change it into an integral and see if that integral converges. If it does, then that means the series is good, also converges. That's what the test does. Okay, so example 1. So apply the integral test to the series all right, so you can see this is going to be decreasing, right? The bottom is bigger. So as n gets bigger, this is going to go to 0. So yeah, it's decreasing for all n, 1 to infinity. It starts at 1. So we're going to rewrite this as an integral. So find the integral from 1 to infinity of x over x squared plus 1 dx. And then we cannot use the improper notation. Of x over x squared plus 1 dx. Oops, forgot my integral symbol. 1 to b. So what kind of integral is that? I'll make it prettier. Oops, how should we integrate this? Yeah, u sub should work. Du is 2x dx. Du over 2 is x dx, which is on the top. So that'll be the limit as b goes to infinity of the integral 1 to b du over 2 divided by u. Pull out the 1/2. That'll be the integral from 1 to b of du over u, which is space 1/2 limit b goes to infinity of ln of u from 1 to b. Change u back to x. That'll be ln of x squared plus 1 from 1 to b. So that will be the limit. B goes to infinity of ln of b squared plus 1 minus ln I'm going to put a bracket before the limit just to save space here. That's 1/2 right there. Okay. So this would be ln2, right? Where's this going to be? When I take the limit. You see? If b goes to infinity, what happens to this log? No, it's just this whole thing goes to is infinite. It's just super huge. So the limit will be infinity, which means the integral diverges. So since the integral diverges, then so does the series by the integral test. That makes sense? Because the point wasn't to do the integral. The point was to figure out what the heck is a series doing. So you look at the integral to figure out what this is doing. Any questions on the first example? 9.3. All you do is take an integral and see if it converges. And then that means the series converges. Nothing else. Guess so. So there's one last example. Let me write down the next test first, and then we'll do one more example and we'll call it a night. This is called the P series. This is the easiest test in my opinion. Convergent convergence of P series, right? The P series from n equal 1 to infinity, 1 over n to the P converges for P greater than 1. And I'm sorry. Yeah, that's right. And diverges for P between 0 and 1 and equal to 1. Basically, if P is 1 or a fraction that's less than 1, then it diverges. So, for example, determine the series converges or diverges. So sometimes they might not give you a actual series. You have to figure it out yourself. So what is the pattern here? Right, this is going to be, is the bottom is increasing by 1, right? The top is the same. So you agree that this is 1 over n, right? Starting at 1. 1 over 1 is 1. 1 over 2, 1 over 3, right? So this works. So sometimes you need to find this yourself. So since P is equal to 1, then the series diverges by the P series test. Does that make sense? So we had another one, let's say, it's real quick. 1 over n to the 3 halves. You would say since P is equal to 3 over 2, which is greater than 1, then the series converges by the P series test. The P one's pretty easy, right? You just look at the power. So, but the thing you should always do first, which I didn't do here, but later when we have just a random series, and I'll tell you what the test is. Check the limit of the sequence first. Limit 0, then cool. I guess we'll stop here. Think some questions on Wednesday, yeah?
Can you drag down the page just a little?
Yeah,
Is it-
sure.
Ah, right there. That's okay.
So we can divert from on the graph will against 1 point, or what that means about the bird.
For series, basically, the sum will be infinite, so it never actually stops. Like, for example, if you look at 1 over n,
One over n goes forever. Right?
Well, for a sequence, it's a little bit more clear. All it is the limit. If you look at a sequence, if the limit is finite, then that's where it stops.
Mhm.
Eventually, the terms get like smaller and smaller and smaller. But for a series, the question is like, if I add all these little pieces, do I finally get a sum? Does it stop somewhere? Does the sum happen? These examples, some of them, most of them, I should say, nobody has actually found the sum, but we know that they have. We know that there is a total partial sum. So theoretically, we've proven that there is an nth partial sum. If you look at the first definition for series, there's a lot back. You guys put that beside or? Go back a little bit. Right here, this first thing we talked about. The series of partial sums, right? So we know that there is a partial sum that converges. We just don't know what the total is. So these tests can verify, yeah, this exists. But trying to find what that number is very difficult. There's been some people that pick a series and they try to find it for years, never find it. I think some guy found one over n squared. Let me see. I think it's a famous one. The sum of 1 over. Yeah, let's see here. Yeah, here it is. This is the Basel problem. So someone over n squared was actually found. So that limit n goes to infinity, but the sum ends up going to 6 over pi squared, which is the inverse solution of the Basel problem, Basel. So finding these numbers is tough, but we can prove that this guy converges. Like we knew that because of the P series. Finding that number is not easy. I think some people are trying to find n cubed. Sometimes that happens because there's a mathematician go crazy going on a path that ends up going nowhere. But anyway,
They might have fun.
but yeah, we'll talk. Yeah, infinite time. Yeah, this one was found in 1735. All calculated, man. Trying to figure out who found it though. I think it was, oh, it was Euler. Of course it was. All right, guys, have a good night. We will stop here.
All right, we'll see you. Thank you.